All right, so recall that last time we started talking about different notions of convergence. So we said that in measure theory, if you have a sequence of measurable functions, there are several different ways in which they can converge. Of course, when you were doing your BSc, you learned of sequences of functions which converge pointwise. And you probably learned of sequences of functions which converge uniformly. Anyway, you can also talk about what it means for a sequence of functions to converge almost everywhere. And there's another notion which is called convergence in measure. And it turns out that these notions have their parallels in probability, and those are of some importance also. And so that's what we are about to talk about. That's what we're talking about right now. Last time, what we did is we stated the definitions of convergence almost everywhere, convergence in measure, convergence in NP. We made a statement as to this implies that implies this along a subsequence, and this other thing implies that. But we haven't proved that particular proposition yet. That is part of the thing we're going to do. So without further ado, let me turn off the camera and switch to the iPad screen. All right. So last time we wanted to motivate convergence and measure, and we motivated convergence and measure using this particular example. We constructed a sequence of functions as follows. All the action is taking place on the open interval 0, 1. The sigma algebra is the Borel sigma algebra, and the measure is simply Lebesgue measure on 0, 1. Now what I'll do is I'm going to construct a sequence of functions as follows. First I'll have two terms where I break up 0 to 1 into two halves, 0 to a half and half to 1. And here in the first case, I take f to be, or f1 to be 1 on the first half, 0 on the second. In the second function, I take f2 to be 0 on the first half, first 1 on the second. Then I will break up the interval from 0 to 1 into 4 pieces. So I'll have 4 functions, f3, f4, f5, f6. f3 is 1 on the first quarter, 0 everywhere else. f4 is 1 on the second quarter, 0 everywhere else, and so on. Then I will have a string of 8 functions because I will break up the interval from 0 to 1 into 8 pieces. And I will continue in this fashion. And as you can see that this sequence of functions will not converge anywhere pointwise. Because if I pick any x, and as I move along the sequence, there will be some term in the sequence where the function is 1 at x, and there will be many terms where the function is 0 at x. So in other words, this function will not converge anywhere. However, we somehow see that we ask ourselves, okay, as n is getting large, for most of the time, the function seems to be 0. So is there any sense in which fn converges to 0? And the answer is yes. So the thing is, if you ask yourself, let me fix an arbitrary epsilon. Now let me look at the set of points where the difference between fn and 0 is more than epsilon. And let me look at the measure of that set. Well, the measure of that set in this case does go to 0 because you can see that the set of points where the function is 1 keeps getting smaller and smaller. Motivated by this, we made the following definitions. We stated this for measure spaces. We said that automatically you can translate it for probability spaces by just changing the names a little bit. Okay, so omega f mu is a measure space. Let fn and f be measurable functions from omega to r. We'll say that fn converges to f almost everywhere, or mu almost everywhere if we want to emphasize the measure. If you can throw away a null set, and on whatever is left, fn converges to f. In other words, if there exists a set n in f with mu n equals 0, such that once you throw n away, in other words, for all omega and omega minus n, you have f and omega converges to f omega as n goes to infinity. Then we said that fn converges to f in measure if, for every epsilon greater than 0, if I look at the set of all omega and omega, where the difference between f and omega and f is more than epsilon, and then I look at the measure of this set, the measure of this set keeps getting smaller and smaller as n goes to infinity. Finally, we said suppose fn and f have the property that if I take their absolute value to the pth power and integrate, I get something finite. Okay, and here 1 less than or equal to p less than infinity. I'll say that fn converges to f in LP if the integral absolute value fn minus f to the p goes to 0 as n goes to infinity. Then we said we're going to explore the relationships among these notions of convergence. The first proposition we made, we stated this proposition, and I think we have already proved the first part. Notation is as before, I have not written it. Okay, so omega f mu is a measure space, blah, blah, blah. So the first one says the following: suppose mu of omega is finite. In other words, suppose that you're on a finite measure space. In particular, this will be true on a probability space. If fn converges to f almost everywhere, then fn converges to f in measure. We proved this last time. Then we stated this thing, this we have not proved, we're going to prove it today. If fn converges to f in measure, then there is a subsequence fnj such that fnj converges to f almost everywhere. And the third is that suppose integral absolute value fn to the p is finite, integral absolute value of f to the p is finite for some p in 1 infinity. If fn converges to f in LP, then fn certainly converges to f in measure. Okay, I also mentioned last time that this is not the last word in terms of what type of convergence implies what. There are more statements you can make, but these are the ones we're going to work on. So as I mentioned, 1 has been proved. Now we're going to prove 2 and 3. All right. All right, so now let's prove 2. 2 says that convergence in measure implies convergence almost everywhere along a subsequence. Okay, so let's prove this. So suppose fn converges to f in measure. Okay, then what I'm going to do is I'm going to say let n1 be 1. Okay, and what I'll do is I'll choose n2 greater than n1 such that mu of the set of all omega in omega, where absolute value of fn2 of omega minus f of omega greater than 1/2 is less than or equal to 2 to the minus 2. Then I will choose, let me bore you a little bit with this and then we'll see what the pattern is. Choose n3 greater than n2 such that mu of the set of all omega in omega such that absolute value of fn3 of omega minus f of omega greater than 1/3 is less than or equal to 2 to the minus 3. Then choose n4 greater than n3 such that mu of the set of all omega in omega such that absolute value of fn3, not n3, n4 of omega minus f of omega greater than 1/4 is less than or equal to 2 to the minus 4. Okay, now I've tried your patience enough. Let's see what the pattern is. So actually, if you want to make this proof look a little nicer, what I can do is I'll just put this in brackets. So this is just illustration of what I'm about to write next. So next I will make a statement in terms of just j minus 1 and all. As you can see, the next statement will be more elegant than these sentences we wrote down. But if you're wondering what the next statement means, well, it means exactly the sentences that we wrote down. We're not done here, so this cycle continues. All right, so what is the basic pattern? Here is the basic pattern. All right, so choose nj greater than nj minus 1 such that mu of set of all omega in omega such that absolute value of f nj of omega minus f of omega greater than 1 over j less than or equal to 2 to the minus j. Okay, so in a nutshell, this is what we're doing. Okay, So the 4-sentence, 2, 3, 4 sentences we wrote above were just illustrations of this. So what you're going to do, you'll take n1 to be 1. So basically what that's saying is that, so remember, you're looking for a subsequence which converges to f almost everywhere, right? So basically you're looking for this subsequence, fn1, fn2, fn3, ... such that fnk converges to f almost everywhere as k goes to infinity. This is what you're after, right? Okay, so now what I'm saying is we'll take fn1 to just be f1. Now remember, what do you know? You know two things. Well, actually you have, I don't know, maybe you know many things, but there are two things you have to keep in mind. First of all is that for this to be a legitimate subsequence, n1 must be smaller than n2, n2 must be smaller than n3, n3 must be smaller than n4, and so on. The second thing is, you know from the definition of a convergence in measure that, I'll use a different color. Let's say I think of this as epsilon. What convergence in measure says is that the measure of this set can be made arbitrarily small. So what I'll do is, for any j, I will insist that the measure of this set with epsilon equals 1 over j be less than or equal to 2 to the minus j. Okay, so this is basically something that just follows from the definition of convergence in measure. Convergence in measure says that for any epsilon, you can go far enough into the sequence such that after that, this measure can be made arbitrarily small. And so here you want it to be smaller than 2 to the minus j. This part is there solely to ensure that n1 is strictly less than n2, n2 is strictly less than n3, n3 is strictly less than n4, and so on. And so, in fact, you have a legitimate subsequence. So that's why these two parts are there. Where am I now? Okay. All right, so this is what you do. Do you agree that we have come up with a subsequence? Now, at this point, you may not be convinced that the subsequence is of any use, but I hope you agree that we have come up with a subsequence, because we have come up with a subsequence of the natural numbers, n1, n2, n3, and so on. Okay, so this gives us a subsequence f and k going from 1 to infinity. And now we claim that this subsequence has the desired properties. Okay, I've been using j everywhere, right? So why don't I just stick to j? Okay, so now we claim that f and j converges to f almost everywhere as j goes to infinity. Okay, so how do we prove this? So let aj be the set of all omega in omega with the property that f and j of omega minus f of omega is greater than 1 over j. And then suddenly you realize that, okay, this set that I'm talking about is precisely the set that we had here. All right, so now what do we know? We know that mu aj is less than or equal to 2 to the minus j. Because remember, all we have done is this set that we had here. Now we've just given it a name. We're calling it aj. Okay, so we have mu of aj less than or equal to 2 to the minus j. And now, of course, remember, 0 less than or equal to mu aj less than or equal to 2 to the minus j. So what you're going to have is 0 less than or equal to the sum j going from 1 to infinity. J going from 1 to infinity, mu of aj less than or equal to the sum j going from 1 to infinity, 2 to the minus j. And this thing, of course, is, let's see, it starts at 1/2. So this is just going to be 1, which is finite. You guys with me so far? Okay, so the important thing is here. the sum j going from 1 to infinity mu of aj is finite. All right, now we will use Borel-Cantelli. All right, what did Borel-Cantelli tell us? Okay. Maybe I stand corrected. When I stated Borel-Cantelli, I stated it in the context of probability spaces. However, if you look at the first half of Borel-Cantelli, this also works for measures. Okay, let me repeat that. I stated Borel-Cantelli for probability spaces. However, the first part of Borel-Cantelli works also for measure spaces. Let me make a quick note of that, and let me leave that to you to verify. So here is, I'm calling this a homework. You should do this. I am not going to collect this homework, but you should do this just to make sure you understand things properly. Okay, so here's what I'm saying. Let omega f mu be a measure space. All right, and let an n going from 1 to infinity be a sequence of measurable sets. Again, this is the result I'm writing now in this light blue color. This is an analysis result. It has nothing to do with probability. Then the claim is the following. If sum n going from 1 to infinity, mu of an is less than infinity, then mu of lim sup an equals 0. Okay, so I'll leave it to you to do this. I strongly recommend you do this. Please just go through it line by line. It's really not difficult. When you go through this, you will realize that over here, you are nowhere using any notions of probability, except that probabilities are measures. And you're not using finiteness of measure, you're not using independence, etc., etc. So this is true. Second part, of course, I don't know how to make sense of it in analysis, because in analysis, I don't know what independent means. Okay, so the second part of Borel-Cantelli is a legitimate probability result. The first part you can think of as an analysis result, and in particular, probability result. Okay, so I'll leave it to you to do this. And I don't want to go through that detail. Let me just say, here's where we are, right? Okay, and now what I'll say is, let me just say in quotations, Borel-Cantelli, okay? I think you know what I mean here. You have the recorded lectures. I don't know a better name to call this. By Borel-Cantelli 1, basically I'm talking about the Borel-Cantelli for measures, if you like. By Borel-Cantelli 1, mu of lim sup of an is 0. So far, so good? Okay, so now what do we have? Let's write this out in more detail. Thus, mu of the intersection n going from 1 to infinity, the union k going from n to infinity, ak equals 0. All right, so now I'm going to make a claim. I claim that let n be intersection n going from 1 to infinity, union k going from n to infinity, ak. All right, so we claim, basically we're going to claim that if you take any omega which does not belong to n, okay? If you take any omega which does not belong to n, then you do in fact have that convergence of that particular subsequence. So we claim that if omega is in omega minus n, then fnk of omega converges to f of omega. Okay, let me just sneak in a note here. Remember, n is a null set, okay? N is just this set right here. We have given it a name. Okay, so mu of n is 0. So we claim that if omega is outside of n, so it is an omega minus n, then fnk omega converges to f omega. Let's check that this is true. So indeed, suppose small omega is in omega minus n. Okay, in other words, small omega is missing from this intersection. Now remember, for a point to be missing from the intersection, it should be missing from at least one of the sets in the intersection. Okay, so suppose omega is in omega minus n, so it is missing, it is missing from the intersection. If it's missing from the intersection, it's missing from at least one of the sets in the intersection. So hence, omega is missing from the union k going from n to infinity ak for some n greater than or equal to 1. All right, and now you'll see that we're done. Now you'll say, okay, if omega is missing from a union, it's missing from all of them. I.e., no, this is not i.e., this is implies. Thus, omega, okay, thus, there exists n greater than or equal to 1 such that for all k greater than or equal to n, we have omega not an element of ak. Do you agree with that? Right? What have we shown here? We have said that there is some n greater than or equal to 1 such that omega is missing from the union ak going from n to infinity. In other words, there is some n greater than or equal to 1 such that for every k greater than or equal to n, omega is missing from ak. So that's what we're saying here. There exists n greater than or equal to 1 such that for all k greater than or equal to n, we have omega not in ak. Okay, and so now as you'll see, we're done. So thus, for every k greater than or equal to n, we have, so omega is not an ak. Okay, so if omega is not an ak, that means this condition should be violated. In other words, this quantity here, this condition should be replaced by less than or equal to. This is every k greater than or equal to n, we have absolute value of fnk of omega minus f of omega is less than or equal to 1 over k. And hey, this is enough to ensure that f and k omega converges to f omega, right? Because what you've been told is that for k big enough, the error between f and k omega and f of omega is no more than 1 over k. So as k gets bigger and bigger, this error gets smaller and smaller and it goes to 0. Hence, f and k of omega converges to f of omega as k goes to infinity. Any questions with this? All right, so what we've done is we have in fact found a subsequence which converges to f almost everywhere. Okay, so that takes care of parts 1 and 2, and now we need to take care of part 3, right? So suppose the integral absolute value of fn to the p is finite. Integral absolute value of f to the p is finite. For some 1 less than or equal to p less than infinity. And suppose integral absolute value of fn minus f to the p goes to 0 as n goes to infinity. Right, so what do we want to show? We want to show that fn converges to f in measure. Okay, so let epsilon greater than 0 be given. Okay, now look at the integral absolute value of fn minus f to the p. Actually, I want to do the following. No, actually, this is fine. So this is going to be greater than or equal to integral absolute value of fn minus f to the p indicator absolute value of fn minus f greater than epsilon. Do you agree with this? So the thing I'm highlighting in green and the thing I'm highlighting in yellow are both non-negative functions. Okay. The thing that is there in yellow is there on both sides. But on the right side, there's also an indicator function. So this inequality will certainly be true, because suppose that this indicator function is 0, then this quantity is certainly greater than or equal to 0. No problem. And suppose this indicator function is 1, then this quantity certainly equals itself. Okay. And so here I'm using the fact that, okay, so let me actually backtrack a bit. So note that absolute value of fn minus f to the p is greater than or equal to absolute value of fn minus f greater than epsilon. Okay. And now you use the fact that when you're talking about non-negative functions, bigger functions cannot have smaller integrals. Okay, now let's look at this thing. Okay, so this is going to be greater than or equal to integral epsilon to the p indicator absolute value of fn minus f greater than epsilon. Now remember, nobody is saying that fn minus f to the p is always bigger than epsilon to the p. We are not saying that. However, what we do know is that on this set, okay, which I've highlighted, it is true that absolute value of fn minus f to the p is greater than or equal to epsilon to the p. So once I put these indicators, this statement is true. Because if both the indicators are 0, then you get 0 greater than or equal to 0, which is true. And if this indicator is 1, of course this indicator is 1. And that means your point omega is in this set. Now on this set, fn minus f is greater than epsilon. So fn minus f to the p is greater than epsilon to the p. So this is a true statement. Okay, and now let's look at what we have here. So this is going to be simply epsilon to the p, and then I'll have mu of absolute value of fn minus f greater than epsilon. Okay, so let's see what we have. Thus, a mu of absolute value of fn minus f greater than epsilon is going to be less than or equal to 1 over epsilon to the p integral absolute value of fn minus f to the p. Now remember here epsilon is fixed, okay? And right, in convergence and measure, you say let epsilon greater than 0 be given. Now prove something. So epsilon greater than 0 has been given. So epsilon greater than 0 is fixed. And now you look at the right side, this certainly goes to 0 as n goes to infinity. And so you're done. So mu of fn minus f greater than epsilon does go to 0 as n goes to infinity. So fn does converge to f in measure. Any questions with this? All right. There are a couple of quick comments. So let omega fp be a probability space. Let xn, n going from 1 to infinity, x be valued random variables on omega fp. And I will leave it to you to fill in the gaps here. Xn, oh. Okay, I'll leave it to you to write this out, but let me just say analysis, convergence almost everywhere is the same as convergence almost surely in probability. And in analysis, convergence in measure is the same as convergence in probability. Okay, so actually I'm thinking since this is going to be important enough, let me actually write down a definition of convergence in probability. As I've said, this is redundant because we have already talked about how convergence in probability is defined, but since this is going to rear its head, might as well take care of it. Okay, so that's fine. Okay, so now say that xn converges to x in probability, all right, if for every epsilon greater than 0, if I look at the probability of the set where absolute value of xn minus x is greater than epsilon, then that goes to 0 as n goes to infinity. Okay. Now, of course, remember that when I write p of absolute value of xn minus x greater than epsilon, this is shorthand for p of set of all omega n omega with the property that absolute value of xn omega minus x of omega greater than epsilon. Okay. So remember that the thing I'm highlighting in yellow is short for the thing I'm now highlighting in green. All right, so I wanted to state the definition of convergence and probability because this is important. As you can see, this is just taking the definition of convergence and measure and just writing it in terms of probabilities. Any questions so far? All right, so the next order of business is LP spaces. Now, all of you have had some exposure to functional analysis. And so my guess is that some or much of this you have done. Actually, why don't I get some feedback from you? Have you done LP spaces in functional analysis? Yes, no? LP spaces. Have you done LP spaces in functional analysis? Anybody? Yes, you have done it. Okay. All right. So that is good. Somnath, did you take functional analysis here, or do you,
Yes, sir, I have to here also.
what's that?
I have to here also.
Okay. Okay. I just want to be sure because different places may have slightly different syllabus. So I just want to make sure that here it is covered. Okay. All right. So then maybe in LP spaces we'll do it, but we may spend a little less time on it. Okay. But when they taught you LP spaces, did they teach you how to do measure and abstract measure spaces, or no? Or did they just do it on the real line? What did they do? No response. All right. That's fine. Okay, so our treatment of LP spaces will not be complete. Okay. That's a bad joke, but the LP spaces will be complete. All right, so let mega f mu be sigma finite, a measure space. Okay, so for a function f, taking omega to r bar, which is f b of r bar measurable, define, right now I'm just going to call it a symbol. Right, this looks like norm f sub p, but right now I don't know that it's a norm. So I'm just going to call it this symbol by integral absolute value of f to the p be mu to the power 1 over p. If p is in 1 infinity, note that the interval is closed at 1, open at infinity, and this symbol, which looks like norm f infinity, equals the infimum of k greater than or equal to 0, such that mu of the set of all omega in omega, such that absolute value of f of omega greater than or equal to k is 0. Okay. All right, so right now I'm just defining these symbols. It uses this norm notation, and so maybe you already are starting to suspect that these things are going to end up being norms, and they are going to end up being norms. But we don't know that yet. Okay. All right, so what do I do if p is in 1 infinity? So if 1 less than or equal to p less than infinity, and I have any f taking omega to r bar, which is measurable, I will define this symbol, which looks like norm f p, to be I take absolute value of f to the pth power, then I integrate it, and then I take the pth root of that. Okay, and I'll define this symbol, which looks like infinity norm of f to be the infimum of all k's, with the property that the measure of the set where mod f of omega greater than or equal to k is 0. Okay, so another way you can translate this thing into words is, what this is saying in words is that absolute value of f of omega less than k mu almost everywhere. Right? Because you're saying that the set of points where absolute value of f of omega is greater than or equal to k as measure 0, which means that on the complement of that set has full measure. All right, so that's what we'll do. Next thing I'll claim is the following. Note that the quantities, this symbol for p in 1 infinity are well defined, though they may be infinity. Right? And you can see why this is true. Right? If I take a measurable function, I take its absolute value, and I take any power, and I integrate it, I'm integrating a non-negative measurable function. The worst thing that can happen is I'll get infinity. I'll get infinity, or I'll get some finite non-negative number, but I will never get infinity minus infinity. So this will always be well defined, in other words, meaningful, though it may be infinity. And here what you're doing, here you're saying, is there a number k greater than or equal to 0 such that absolute value of f of omega is less than k mu almost everywhere? Is there such a number k? If there is such a number k, then this infimum will be finite. And remember, this k is greater than or equal to 0. And if there is no such number k, then the infimum will be infinity. Okay, so these two quantities are always well defined, though they may be infinite. All right, so now we can define what we mean by LP space. So for any p in 1 infinity, let LP of omega f mu equals LP of mu equals the set of all f taking omega to r bar, such that f is measurable and norm f sub p is less than infinity. All right, there you go. That's what your LP space is. Okay, so LP of omega f mu, which I can also write as LP of mu, is simply the collection of all functions f taking omega to r bar such that f is measurable and this symbol is finite. Namely, the p norm of f is finite. All right. Here's a quick note. So note that for p in 1 infinity, and note that here I've excluded infinity, okay? The measurable f taking omega to r bar is in LP if and only if integral absolute value of f to the p d mu is less than infinity. All right, so this is not really news to you, right? I mean, this just follows from the definition, right? If p is in 1 infinity, infinity is excluded, and I have a function f taking omega to r bar which is measurable, then it's going to be in LP if and only if the integral absolute value of f to the p d mu is finite, right? Because remember, the pth root of something is finite if and only if the thing is finite. So if this thing is finite, its pth root is finite, and so this is finite. If this is finite, then the pth root of this is finite, and if the pth root of this is finite, then this itself is finite. Okay, so I'll just leave it to you to think about that. It's not very deep. It's a simple idea. All right. So this is what LP is. Okay. So LP of omega f mu is just the collection of all f taking omega to r bar such that f is measurable, and this symbol is finite. I'm being a little reluctant to call this a norm because we haven't yet shown it's a norm. And to do that, we have to do a little bit of clever footwork, but we'll come to that. Okay. So the first thing I claim is that this LP is a vector space. So here's a lemma. For any 1 less than or equal to p less than or equal to infinity, LP of omega f mu is a vector space. All right, now I'm only going to do the case when p is finite. I will leave you to fill in the details for the case when p equals infinity. Okay, so proof, right? So let f g be an LP of omega f mu, right? Let alpha be an R. All right, so what do we need to do? We need to show that f plus g is an LP and alpha f is an LP. Right? If we do these two things, then we have shown that LP of omega f mu is indeed a vector space. By the way, LP of omega f mu, we may also write as LP, depending on the circumstances, we may write as LP of omega if f and mu are understood. We may write it as LP of mu if we want to put the emphasis on the measure. But remember, once the measure is there, omega and f are fixed, right? Because a measure is not defined in a vacuum. A measure is defined on some measurable space, omega f. So as soon as I tell you I'm talking about the measure mu, I'm fixing omega and f also. And of course, very often when there are no competing measures and no competing spaces in the background, and there's only one set omega and only one measure and only one sigma algebra, we just write LP. Okay, so when everything is understood what the measure space is, we'll just write LP. Okay. We need to show that f plus g is an LP and alpha f is an LP. So what we'll do is we'll first consider the case. One less than or equal to p less than infinity. All right. Okay, so now basically I want to show that f plus g is an LP. Okay, so what am I going to do? So I want to show that f plus g is in LP, I want to show that the integral absolute value of f plus g to the p is finite. That's what I want to show. Right? So let's do the following. Suppose I look at absolute value of f plus g. This is less than or equal to absolute value of f plus absolute value of g. This is triangle inequality. Okay. So absolute value of f plus g to the pth power is going to be less than or equal to absolute value of f plus absolute value of g to the pth power. And I claim that this is less than or equal to 2 to the p absolute value of f to the p plus 2 to the p absolute value of g to the p. All right, now let's see why this equation is true. All right. Okay, so here I'm adding absolute value of f and absolute value of g. Now there are two possibilities, right? Either absolute value of f is greater than or equal to absolute value of g, or absolute value of f is less than absolute value of g. So suppose absolute value of f is bigger. That means absolute value of f plus absolute value of g is no more than 2 times absolute value of f. So this thing is less than or equal to 2 times absolute value of f. And now take the pth power, so I'll get 2 to the p absolute value of f to the p. The other possibility is that g, the absolute value of g is bigger. In that case, absolute value of f plus absolute value of g is no more than 2 times absolute value of g. So absolute value of f plus absolute value of g to the pth power is less than or equal to 2 to the p absolute value of g to the p. So if I add these two upper bounds, that will certainly be an upper bound for the left side no matter what. Okay. So this is what you get. So this implies that integral absolute value of f plus g to the p is less than or equal to 2 to the p integral absolute value of f to the p plus 2 to the p integral absolute value of g to the p. And now remember, this guy is finite. Why is it finite? Because f is in LP. You already know that. And this guy is finite. Why is it finite? Because g is in LP. You already know that. And so this thing is going to be less than infinity. All right, so we have proved that f plus g is in fact in LP. The other one is quite straightforward. So now alpha is a scalar, so I'll take absolute value of alpha f to the p. This is just absolute value of f to the p, absolute value of alpha to the p, absolute value of f to the p. And so when I look at integral absolute value of alpha f to the p, this is going to be absolute value of alpha to the p integral absolute value of f to the p. Right, and this is true because you can pull out constants, right? And then remember that this is finite because f is an LP. So this thing is also finite. And so alpha f is also in fact in LP. All right, so we have shown that LP is in fact a vector space. By the way, let me make a note. I'll leave this as a do-it-yourself exercise, case p equals infinity. Any questions so far? All right, so now the thing is we have been using this norm notation, and somewhere we already know, because we know some functional analysis, that this thing that we have been very hesitantly calling a norm is actually going to be a norm. But some little things need to be ironed out before that. So let's do all that ironing, and before we do the ironing, let's remind ourselves what a norm is. Okay, so this will be familiar to you. I'm taking only vector spaces over the real line. Okay. So a norm, I'll use this symbol, on a real vector space, V is a function norm taking V to R such that the following properties hold. First is norm of x is greater than or equal to 0 for all x in V, and norm of x equals 0 if and only if x equals 0. By the way, this is the 0 vector, okay? This is not the number 0, this is the 0 vector in V. So that's the first property. Second property is that norm of alpha x equals absolute value of alpha norm x for all x in V, alpha in R. Okay, this is something you expect of a norm, right? Norm of 4 times a vector is 4 times norm of the vector. Norm of minus 3 times a vector is 3 times norm of the vector. And the third is the triangle inequality. So norm of x plus y is less than or equal to norm of x plus norm of y for all x, y in V. Okay, so these are the 3 requirements for the norm. Now, here's what is going to happen. I have about 1 minute left, so I have to say this at record speed, or I have to say a little bit now and leave the rest for next time. So I think I'm going to do that. So here's what's going to happen, okay? We will see that because of the strange things that happen in Lebesgue integrals, if norm of f sub 1 is 0, all you can say is that f is 0 almost everywhere. And so we're going to run into trouble here, because we will have a situation where norm f is 0, but f is 0 only almost everywhere. And so then we will do a little bit of clever footwork. What we will tell ourselves is that, oh, you know what? We'll think of LP not as collections of functions, but as collections of equivalence classes. And the equivalence class of 0 is the collection of functions, which is 0 almost everywhere. Then once we do that little dance, this thing will actually become a norm, and that's what we're going to do. So anyway, just a spoiler alert, that is what is going to be coming. We will find that if the norm of a function is 0, all you can conclude is that it's 0 almost everywhere. And so in olden times, you might not have legitimately considered that the 0 function. But now we'll say that, okay, we'll work with equivalence classes, we'll identify all functions which are equal almost everywhere. Once you do that, this function, which is 0 almost everywhere, is the same as the 0 function, and we'll happily go on our way. Okay, any questions? All right, so I'll stop the recording right there, and I shall see you next week.